Hi, and welcome to the first installment of a series we're going to be doing on white paper presentations, where we'll take a white paper, which is like an engineering document or technical article, and break it down into an easier to consume media and a presentation. So the white paper we're going to be covering today will be in the description below, but it's titled How to Select a Power Inductor for Point of Load or POL Power Supply. So modern electronics focus on getting everything um, smaller into a lower profile package and all the while being better, more efficient, smarter. Um, and that requires your magnetics and power conversion to enable high power density, um, high reliability, environmental protection, and obviously cost to performance ratio is always important in any project. So these are going to be the 5 steps of designing a POL power circuit. First, we're going to take a look at the design topology. The second is going to be determining the switching frequency that's most appropriate for your application. Third are going to be the circuit parameters. Fourth are going to be the inductor core material. And the final step is the final inductor selection. So step one is the circuit design topology. And to know what kind of circuit you're going to need, you first have to determine the characteristics of that circuit. So some example characteristics I've put in here. If we have an input of 12 volts, an output of 5 volts with a current output of 26 amps, um, you'll notice we're stepping down the voltage. And another name for a step down converter is a buck converter. And conversely, if we were starting with 5 volts and going up to 12 volts, stepping up the voltage, we would use a boost converter. But anyway, we're going to use a buck converter for this application. Since the current is 26 amps, we can achieve that with a single phase, a single inductor. So we're only going to need a single phase for this. But if you had, double this roughly, say 50 amps or 100 amps, you could use a 2 or 4 phase buck converter. So it's just going to scale up that way, roughly how many inductors you're going to need to manage the desired current. And then synchronous is always recommended over asynchronous, but asynchronous uses a non-integrated Schottky diode to help manage the conversion. And the synchronous form is much more efficient because you have an integrated MOSFET into the converter. So you only have the one circuit, one electronic. And then obviously the synchronous allows for a much higher efficiency. So that's most of the reason that we recommend it. So our final design topology is going to be a single phase because we only have 26 amps, synchronous for efficiency, and buck converter. Step two is going to be determining the circuit switching frequency. There are many things to consider when determining the switching frequency, such as space, which is going to drive how high or low you're going to be able to tolerate having the switching frequency, because the higher the switching frequency, the smaller the space, which is a plus. But higher switching frequency also drives up switching loss and driver loss, which is going to affect your power conversion efficiency. And then power density. And so usually with these 3 considerations, modern electronics, with the way these interactions are currently working with current MOSFETs, etc., are usually in the hundreds of kilohertz for kind of an optimal balanced switching frequency. Obviously, if you favor space over conversion efficiency, you're going to be above that, maybe into the 800-900 kilohertz or even into the megahertz area. Or conversely, again, if you favor efficiency and you have plenty of board space to play with, maybe you're in the low thousands or maybe even upper hundreds would be fairly unusual. But if you're seeking one of those space versus conversion efficiency well above the other, you'll kind of end up in these fringe areas. So for our example purposes, we're going to stick kind of right in the middle. We're going to use 500 kilohertz. So step 3, we're going to be determining some circuit parameters via calculation. So the first one we're going to take a look at is duty cycle, which is basically the time that your converter is sort of switched in the on position um, over the total time um, that can span. So basically, it's on over on plus off time, and that's going to be the same ratio as your voltage out divided by your voltage in. So if you'll remember, we had selected 5 volts out, 12 volts in, and we're going to end up with a duty cycle of 0.417. Our second calculation we're going to take a look at is the ripple current. Um, and so when you're turning on and off the converter, you're going to have kind of a ripple occurring in the current. You can kind of see it down here in this diagram, the blue line being the current, and the black line being kind of our determined current target that we want it at. So you're going to be above that at times and below that at times. And so the ripple current is basically determining how far above or how far below we're willing to tolerate that as a proportion to our target current. So for this example and for general purposes, it's usually around 30% or zero point 0.3 of the target output current. Um, but again, that can somewhat vary based off your specific application. But it's a pretty good rule of thumb is 30%. So then obviously it's a fairly simple calculation there. You just multiply 26 by 1.3 and then by 0.7 to determine your IL max and IL min, um, and by 0.3 to determine the absolute ripple. So we've got 7.8 amps as the ripple current, 29.9 amps, as you can see here, for the maximum, 22.1 amps for the minimum. All right, now that we've finished up the circuit parameters, we can move on to step 4, which is the inductor core material selection. So in the table on this slide, you've got 3 fairly similar inductors. All of them are 1 microhenry or 1,000 nanohenries plus or minus 20% on the inductance. So they're all going to feature the same energy storage capability. As you look at the DCR, which is at the bottom of the table, the ferrite core, which is the first option, has by far the lowest at 0.42 milliohms. And then moving over one to the right, the iron powder core is second lowest with 1.06, and then the alloy powder core is the highest with 2 milliohms. So they kind of double each time you go over to the right on this chart. Um, Another key difference between these materials is that the ferrite cores in general will always have what's called hard saturation. So when they get to the saturation current, you can see here kind of in the middle of the table, it's 40 amps for this ferrite core, which gives us plenty of built-in space over the 29.9 amp max from the ripple current calculation we did earlier. So we're pretty safe here. Um, but you'll notice the iron powder is a little bit closer here and much closer on the IRMS, which is basically thermal uh, performance. But that's less of an issue for the powder cores because they have what's called soft saturation. So instead of performance inductance dropping off very sharply at that saturation point, it just gradually rolls off at that point. Um, so it's less of a concern and more appropriate for applications where you may be seeing an occasional surge in current. Sorry. Um, and you want to have some performance still from your inductor, but maybe you're not necessarily always going to be operating at that current, so you want to optimize the inductor's performance to something much lower with the ability to kind of absorb a big spike. So that's where you would see a lot of the powder applications. And additionally, they can facilitate a much lower profile, a much lower height. So looking at the efficiency benchmarking, as you can see, there's a pretty clear-cut winner. It's the SLM part, which is that ferrite core. Um, Mostly because the space allows for using the pure ferrite, this is kind of going to dominate performance. Like I was mentioning earlier, you're going to see more of the powder applications if you're really pinched down for height, or again to maybe absorb um, an unusual application where you might have some spiking in current. And then likewise, this is the thermal comparison. These are always going to show very similar results, the thermal and efficiency, because heat comes from lack of efficiency, basically. So wherever that power isn't efficiently being converted, it's therefore being converted into heat. So these are going to basically tell you the same thing, but maybe a slightly different flavor if you want to look at it a different way. But again, the SLM part, the ferrite core dominating, um, and the other two kind of following their respective heights, basically. So to wrap this white paper up, I wanted to say that you can skip a lot of the calculation in the middle and even the inductor selection at the end by going to itg-electronics.com. And we have a buck and boost converter tool to help you calculate some of these with the click of a button as opposed to trying to do those all by hand. So I'm going to navigate to this real quick and just give you a demo. So if you'll remember, we were using a buck converter. So this is where you would select, but buck converter, and we were going down from 12 to 5 volts. Our current was 26 amps with a 500 kilohertz switching frequency. Our ripple current, our delta IL, we were using 30%, which what I had said is that's pretty standard, but you can play around with it here, and it gives you the freedom to kind of check how that would affect things without having to redo those calculations over and over again. And we'll put some dimensions in here to kind of give us some apples to apples comparisons as opposed to comparing inductors of wildly different sizes. So once you've entered what you like, you can just click calculate here. And you'll notice these are all the same values we calculated within the presentation earlier, um, with our time on, time off being factored by duty cycle. And then it gives us our recommended inductance of 0.748 microhenries or 748 nanohenries. Oh, so by clicking on that button, we get recommended all of the ITG part numbers that can satisfy the parameters that we've entered above. So from there, it's just narrowing down, refining, maybe going back up and saying, actually, there's a lot of options. Maybe I want 20%. Maybe I want to dial it in a little more. Um, and then you can just keep refining that way until you come to your final selection. Also, if you have any questions or comments that you'd like to submit to us at ITG Electronics, you can do that through the question portal here on our website, and we'd love to help you with any future magnetics needs.